Okay, we're starting Unit 6 on confidence intervals. Today, actually inference for proportions is Unit 6. We're going to start looking at confidence interval for a population proportion. Lesson 6.1 from the AP course and exam description booklet is introducing statistics, Y, B, normal. If we look at that, we are looking to identify questions suggested by variation in the shapes of distributions of samples taken from the same population. That means basically we're going to use the sampling distribution, the distribution of samples taken from the population. So we're going to use that to draw inferences about a population parameter. We know that variation is random, it can be random or not, that our conclusions are uncertain. Recall, all the statistical inference we're going to do is going to be using sample statistics to draw conclusions or draw and make inferences about population parameters. So there's no way we can be 100% sure that our conclusions are correct because we take relatively small samples, measure them, and then use those measurements to estimate or draw inferences, draw conclusions about our population parameter. But we could, just by natural variation due to sampling, we could end up with a non-representative sample and get a bad estimate or draw a wrong conclusion. So we have to be willing to accept a certain level of risk in order to do this. Today we're going to start talking about a confidence interval for a population proportion. That's what our goal is to look at. We're going to talk about what a confidence interval is, but first we'll talk about using sample statistics to estimate a population proportion. A population proportion we generally represent with a small letter p. And for whatever reason, this won't let me do it. Okay, is the true population proportion for whatever the characteristic is that we're measuring. We use the p hat. We insert an equation. Maybe we can do a p hat here. Do we even have an equation editor here? All right. You know what p hat looks like. We're just going to call it p hat. You know what that looks like. This is going to be our sample proportion, and the p is little. When we're doing a confidence interval for population proportion, we're going to let p represent the true population proportion, and p hat represent the sample proportion. Now, the problems that we have are we could have the wrong p hat not be equal to the true population proportion. If we take a sample of size 60 or size 50, and our sample size is going to be the little letter n, we're doing these. We're going to use the sampling distribution for sample size n and the distribution of the p hats to draw conclusions and inferences about our assumptions or what we've been told or what we know or claims about a true population proportion. Potential problems are we could get a bad point estimate. Well, we could get a p hat that's not equal to p. Let's go over here to a little simulation I ran. I actually wrote this code to do a sampling distribution for a population proportion, but by changing the number of samples we do to 1, we can draw just one simple sample. In this code, it's set up to have a sample with a sample proportion or with a population proportion of 40% meeting some condition we're going to call success. And if I run it one time, we get a random sample of 50, using a random sample of 50 here, and we see that even though we know the true population proportion is 40, our point estimate, the p hat that we got with that one sample, was 44. And so that's 4 off, 0.04 off from the 0.4 that we know to be true. So we can get really extreme samples, or we can get really close samples. There's one that's 0.38. Here's 1.42. They're all relatively close so far. Well, I keep hoping we'll get one that will be a little bit farther off. There's one that's 0.06 off. So we could get some really extreme ones. What we could do is generate this, and we could see if we do this 1,000 times, we can get a sampling distribution. Let's say there's one that's 0.5. That's 10% off. There's another 0.48. It's really close or really far away. We could get some really extreme ones. We're not going to spend a lot of time looking through these. I thought I saw 20 something. But we can get small ones. We can get large ones. We can get really big ones or really small ones. We can get some. There's a 0.36. That's not so far off. Another 0.5, a 0.52. There's a 0.54. So you can see that we can draw random samples that aren't very representative of the population itself. We can use the sample distribution like we saw in the last unit to calculate probabilities of getting those samples if the true population proportion is true. But we need a way to try to overcome the very real possibility that our sample proportion is not equal to our population proportion. And the way we're going to do that is we're going to construct what we call confidence intervals. We're going to take our p hat when we calculate it, and we're going to add and subtract. I'm going to do this. We don't have a nice little equation editor here. We're going to add and subtract a margin of error. And so that generates an interval with a lower bound and an upper bound. So in this confidence interval, what we actually do is we present an interval that is likely to contain the true population parameter. We'll talk more in the next section about how we do that and how likely it is to contain it and how we restrict it and how we measure those things and how we determine the likelihood of it containing the true population parameter, in this case a proportion, or how we determine the margin of error. We'll talk about all that in the next video.